Have you ever wondered how complex electronic systems, from a simple thermostat to an advanced aerospace control panel, consistently deliver accurate information? How do engineers pinpoint exactly where a signal is going and what it is doing at each stage, especially when something is not quite right? Engineers trace a measured signal path by systematically following the flow of information from its point of origin through various components to its final destination, using specialized tools and techniques to observe its characteristics at each critical junction. This methodical approach ensures that every part of the system is functioning as intended and that the signal maintains its integrity. The fundamental principle behind tracing a signal path lies in understanding the system's architecture, including its schematics and block diagrams. Each component in a circuit or system modifies an incoming signal in a predictable way. By knowing these expected transformations, engineers can compare actual measured signals against theoretical values to identify discrepancies. This allows them to isolate potential issues like attenuation, distortion, noise introduction, or incorrect amplification. To practically trace a signal, engineers begin by identifying the input and output points of interest. They then use an oscilloscope, a spectrum analyzer, or a digital multimeter to measure the signal's voltage, current, frequency, or waveform at various test points designated on the circuit board or within the system architecture. By moving the test probe progressively along the signal's intended route, they can observe how the signal evolves. For digital signals, a logic analyzer might be employed to visualize timing and data states. A crucial technique in this process is employing a function generator to inject a known, controlled test signal into the system. This allows for a baseline comparison, making it easier to detect any unexpected alterations or losses as the signal propagates. Engineers often refer to this as characterization, where they establish the expected performance envelope of the system under various input conditions. Understanding the transfer function of individual stages is also key, as this mathematical model describes how each part transforms the input into an output, providing a theoretical guide for real-world measurements. Ultimately, tracing a measured signal path is about more than just finding a fault. It is about building a comprehensive understanding of system behavior. It allows engineers to validate designs, optimize performance, and ensure reliability by confirming that the electrical language flowing through the system speaks clearly and correctly from one component to the next, translating design intentions into operational reality.